Morning, class. So we're going to try out making my own video lectures here on my iPad, so we'll see how it goes. But we're going to start with our Chapter 2, so hopefully you all had a good spring break, and now you're back and ready to get started with some new material. So we're going to be talking about functions today and introducing us to this idea. So the phrase A is a function of B simply means that A is determined by B, or A can be uniquely determined by B. So for A to be a function of B, we would be able to tell exactly what A is if we know the value for B. So for example, A is a final exam score for a student and B is their semester grade. In this case, A is not a function of B because more things than just your semester grade and your final exam grade do not have to be the same. You could easily get an A in the class but get a B on the final. Similarly, your semester grade is not a function of your final exam. Once again, this is because there are multiple things that go into your semester grade, not just your final exam. It's very possible to get, as we just said, a B on your final exam but get an A for the semester. The next example here is A is the universal product code for an item at Walmart, and B is its price. If you don't remember, universal product code is the UPC code or barcode. So the universal product code for an item at Walmart is not a function of its price, because if you know the price of a certain item, it does not necessarily tell you which item that is. I believe if you walked into Walmart today, although don't go do this because you're supposed to be staying at home, you would find that there are many products that all share the same price. However, the price of an item is a function of its universal product code. That is the function of the barcode, is to make the code unique to a price. If you know the barcode, you know the price. And then the third example here is A is the length of a rectangle with a width of 5 inches and B is its perimeter. So if we draw a little picture here of our rectangle, we can put A's on the lengths and 5 on the widths. And if we know the perimeter of this rectangle, then we could figure out what the lengths are. So for example, if the perimeter was 30 inches, then we know that we have 5 and 5, so that's 10 inches. So that leaves 20 inches for these two lengths, so A would be 10. So A is a function of B. And similarly, if I know A, I can easily figure out the perimeter. If A was 11, then we take 11 plus 11 is 22, plus 5 is 10, 22 plus 5 is 32, and that would be a perimeter of 32 inches. So B is a function of A because B can be uniquely determined by A. So this is a good example of something we're going to call later a one-to-one function, where each A goes with one B and no other way there. So what I'd like you to do now is pause the video for a moment and try the other three examples here at the bottom of the page. Now that you've had a chance to try those, we can run through the answers for them. So A is the diameter of a US coin and B is its value. This is an example where both A is a function of B and B is a function of A, because every US coin has a different diameter, and so those pair up exactly with their values. This may not be something you know off the top of your head, the diameter of US coin, but if you were to look them up, you would see that a penny has a diameter that's different than any of the others. Therefore, they are uniquely paired together, so both directions is a function. Whereas in number 2, the second one here, A is not a function of B, and B is not a function of A. For adult males, shoe size and age have no correlation. I'm going to assume that most of the adult males in this room, like me, their shoe size has not changed recently, even as they aged. And finally, the last example here is A is a person's age and B is the number of days since birth. A is a function of B because if I know how many days it's been since you were born, I can figure out how old you are. But B is not a function of A Because if I know your age, I do not know exactly how many days it's been since you were born. In fact, there would be 365 or 366 answers, depending on if you were born on a leap year or not. Okay, class, now that we've looked at a few examples of this idea of function, let's start looking at it in a more mathematical sense. So there's a few terms we need to find. First of all, a relation is a set of ordered pairs. A relation can be indicated by a verbal description, a graph, or a formula or equation, a table, or a list of ordered pairs. So it's simply pairing up numbers or words or letters or whatever you want to look at, but it's just a set of ordered pairs. Then a function is a very specific type of relation. So a function is a relation in which no two ordered pairs have the same first coordinate and a different second coordinate. So what this means is every first coordinate uniquely identifies a second coordinate because it only gets paired up with one second coordinate. The first coordinate is called the independent variable because it can be any value. And the second coordinate is called the dependent variable because it depends on the value of the independent variable. So to do one example of this ordered pair idea with something you may that's not numbers yet, let's talk about baseball teams. So the relation is cities to Major League Baseball teams. So a few examples, we can start out with the best baseball team, which is the St. Louis Cardinals. So St. Louis paired up with Cardinals. And then we can talk about some local teams. So we've got the Chicago White Sox. So these are just my ordered pairs, right? I've got a city as the independent variable and a team as the dependent variable. And then we could do Chicago and Cubs. And let's just do another couple examples real quick. So we could do the New York Mets and the New York Yankees. So the question is this a relation a function? So to be a function, remember, every first coordinate can only get paired up with one second coordinate. So if we look here, this would not be a function because if you notice, Chicago gets paired up with two different second coordinates, and so does New York. So that means this is not a function. Okay? If we look at a similar question, but with numerical ordered pairs, if we look at these four ordered pairs here, we'll see that all of the first coordinates are different. Even though the second coordinate gets used every time, the first coordinates are all different. Therefore, this is a function. And if we look at the last example here, we'll see that here all of the first coordinates once again are unique and get uniquely paired up with a y coordinate. So all the first coordinates are different. So this would also be a function. So once again, go ahead and take a few moments, pause the video, and try the three problems on the right. Okay, so now that you've had a chance to try these three problems on the right, let's run through the answers real quick. So the first one here would be a function. So if I write out the pairs here, it's this time the team first, so Cardinals and St. Louis, White Sox and Chicago, Cubs and Chicago, Mets and New York, and Yankees and New York. Notice here, all of the first coordinates are different, so that means this is a function. Another way to think about this is if I tell you that I am thinking of a city that has a Major League Baseball team and it likes Chicago, can you tell me what baseball team I am thinking of with 100% certainty? And because there are two options, you can't, so therefore that's not a function. Whereas if I tell you, okay, I'm thinking of the Cardinals and I ask you to pick, or if I tell you I'm thinking of the White Sox and I ask you what city are they from, you can tell me with 100% certainty which city they're from. Now, if you're not a baseball fan, you might have to look it up, but you would still be able to tell me with the pertinent information exactly which one I'm thinking of. So that's the difference between a function and not. Similarly, in the second problem here, if I told you that I was thinking about the number 25 as my first coordinate, you would not be able to tell me with 100% certainty what y coordinate I was talking about, what second variable I was talking about, because there's two options, 5 or -5. So this is not a function. And similar with the last one, if I told you I was thinking about the number 1, you would not be able to tell me which dependent variable I was thinking about because it could be 2 or 4. So this is also not a function. Okay, so that's how you tell if a set of ordered pairs is a function. They're all relations, but is that relation a function? Now, another way that we can look at sets of ordered pairs, especially ones that are a lot bigger sets, is by looking at their graphs or their equations. So, for example, one way to tell if a relation is a function, if we look at its graph, is by using the vertical line test. So some graphs we've already looked at in this class, at least briefly, as we looked at the circle. Right? We talk about quadratic equations, which make parabolas that look like this. We've talked about absolute value equations that make V shapes when you graph them. And then we could also talk about parabolas that open sideways like this. Now, the vertical line test says that if at every point on your graph you can draw a vertical line and it only touches the graph once, it is a function. So if I add vertical lines to each one of these graphs, you should be able to guess based on the vertical line which ones are functions. So the ones that are functions are the ones where the line only touches once. So that would be the two in the middle here. So the quadratic function, and this is called an absolute value function. Whereas the other two examples, the circle and the parabola that opens to the right, are not functions because the vertical line touches the graph more than once. And the reason this means that we have that these are not functions is because if a vertical line touches a graph more than once, then you have more than one y value that goes with a single x value. Because a vertical line has all the same x values. So in this picture, let's call that 1, -2, and then this one would be 1, 4. Notice how we have the same x value, but the y values repeat. So that's why the vertical line test tells us if something is a function. So this means that we can use our Class Calc app or any graphing utility to tell if equations are functions or not. So for example, if I graph this first equation here in my Class Calc app, and I already forgot what it was. So let's go back to it. Y equals x squared minus 3x plus 7. So y equals x squared minus 3x plus 7. And we can hit this in the upper left-hand corner, the target-looking thing to zoom in our graph, I think. Nope, I was wrong. Take it back. So let's just zoom out a little on our graph. And if we look at this, we can see that it would pass the vertical line test. Anywhere I draw a vertical line on this graph, it will only hit it once. So that would be a function. Okay, so its graph, this one would be a function. Okay, similarly, I could graph the next two. So the next one says x equals y to the third power. So x equals y to the third power. And if we look at that, we can see that that also would pass the vertical line test. Therefore, that would be a function. However, if I try to graph x squared minus y squared, equals 9, you can see that this graph would not pass the vertical line test. If I draw a vertical line, say at 10 here, where you can see the grid line, it would touch the graph more than once. So that means that this it is not a function. So x equals y cubed is a function, but y squared minus x squared equals 9 is not a function. So go ahead and take a couple of moments, pause the video, and try graphing the next three with your ClassCalc app and decide whether you think those are or are not a function. Okay, now that you've had a chance to do that, we can talk about these other three. So the next two are functions, because if you graph them, you would see that they do pass the vertical line test. But the last one, which is a parabola opening to the right, is not a function, because it does not pass the vertical line test. Okay, so now that we've spent some time talking about how to tell if a relation is a function using its set of ordered pairs or its graph, we can start talking about the pieces of the function. So there are two big pieces to a function. You've got your the set of the first coordinates, which we call the domain, and you've got the set of the second coordinates, which we call the range. So this is simply a list of all the first and second coordinates. So if we have a set of ordered pairs, like in this first example, the domain is the set of all the first coordinates. So that's the first number in each of these ordered pairs. So that would be -3, 4, and 5. Notice that even though -3 shows up twice, we don't write it twice. We only list it once. It just gets used more than once in the function, in the relation. Notice this one is not a function because -3 gets paired up with 1 and with 6. However, relations, just like functions, do have domains and ranges, so we can still talk about its domain. Similarly, we can do the range, which is the set of the second coordinates. So if we look at the numbers listed here as second coordinates, that would give us 1, 2, and 6. Notice once again, even though 6 gets written twice, I don't list it twice in my range. Okay, so that's one example where we're using a finite number of items. The second one here says the set of all x comma y such that x equals 5. So that would be all the ordered pairs that look like this, 5 comma blank. So the key here is we only have one option for x, but y could be anything. So our domain is simply the number 5, so I put that in braces. But our range could be anything. So we could write that using the words all real numbers, or we could use the interval notation that we talked about right before spring break that you just had a test on. So the way we write all real numbers using interval notation is -infinity to infinity. Now, once you get done looking at sets of ordered pairs and we start looking at equations, we once again can use our graphs to look at this a little closer. So if we look at the graph x plus 2 equals the square root of y, I can go ahead and graph it here. So I'm going to close out the graphs we were just looking at and graph a new one. So x plus 2 equals the square root of y. Okay, so now when you look at this one I put in the graph specifically to try and show you something that's actually slightly wrong with the ClassCalc app, because this graph is not actually completely accurate. And so to look at that, let's talk about some specific points, specifically over here in the negatives. So for example, this point over here, if I just pick one, says, I don't know, they're all decimals, so let's use the decimal one. So if we look at, for example, this one is saying -3 comma 1. Well, the problem with that is there is no way for the right-hand side of this equation to be negative. So all of these values over here to the left of -2 comma 0 are actually not part of the graph. So those actually don't work. So we're only going to look at this right part of the graph. So if I transfer it to my notes, what the graph actually looks like is a point at -2 comma 0 and then a curve off to the right. Now, once we have the graph of a function, we can look at its domain and range. So the domain is the set of all the x values. So to do the domain, if I look at all the x values, notice there are no x values to the left of this point, and that point is at -2. So what I get is from this line -2 all the way to the right. So that means that my domain would be -2 to infinity. And if we look closely, we want to include -2, right? Because that point is included. So I'm going to put a bracket at -2, comma infinity. Similarly, if we look at the y's, we can think about the idea of, is there a lowest point to the graph or a highest point to the graph? So if I look at this one and I can draw a line at the lowest point, the lowest this graph goes is at 0, and then it goes up forever. So we could say the range, its smallest value is 0, and its largest value is infinity, because it goes on up forever. So that's the idea of how you can find domain and range from a graph. So similarly, I could do the same idea again. If I go to my calculator and I graph the next one, y equals x squared plus 8. So y equals x squared plus 8. And if we look at this graph, first of all, this one is actually fine because the y's can be negative this time, so it's okay to have these values over here. And so we get this parabola. And if we notice, this point is at 0, 8, so I can draw that in my graph. So let's go ahead and draw a little sketch of this, just like we did with the previous one. So we got the point 0, 8, and then it looks like this. So if we try to find this smallest x value, the farthest this thing goes to the left, is there a smallest x value? No. Because this graph, this arrow says it goes to the left forever. Similarly, this arrow on the right means the graph goes to the right forever. Therefore, the domain would be -infinity to infinity. However, with the range, there is a smallest y value at 8, and then it goes up forever. So the range would be 8 to infinity. So go ahead and take a few minutes and look at the problems pause the video, look at these problems on the next page, give them a try, and then we'll talk about them here in a moment. Okay, now that you've had a chance to try these, they work just like the ones on the previous page. So these first two are sets of ordered pairs. So the domain, you simply list all of the x values. So that would be 1, 2, 3, and 4. And the range is all the values, y values. So that would be 2, 4, 8, and 16. This second one is the set of all ordered pairs x comma y where y equals 4. So that would be blank comma 4. So the domain can be anything. So -infinity to infinity. But the range has to be 4. So we do that in braces again. Anytime we're listing a finite number, a small number of options, we use braces. Unlike an infinite option where we're going to use interval notation. The graph of this third value looks like this. There's a point at 5, 0, and then we've got the curve going off to the left. So in this case, for the domain, there is a largest x value, but there is no smallest x value. So the domain would be -infinity up to 5. And once again, 5 is included, so we put a bracket. But similar to the ones we've already done, there's a smallest y value, but no largest y value. So the range would be 0 to infinity. And then the final graph here, if you graph it, looks something like this. It's a V shape opening to the left, and we have the point 0, 0. So if we look at this one, once again, there's a largest x value, but no smallest x value, so the domain would be negative infinity to 0. But there are no restrictions on what the range can be. There's no smallest value because this part goes, the bottom part goes down forever. And there's no largest value because the top part goes up forever. So the range would be negative infinity to infinity. Now that we've talked about domain and range a little bit, we can start adding on some function notation. So that's what we're going to talk about for most of the rest of this section, is the idea of function notation. So we have special notation for how we write functions. And it looks like this. So we've got f of x is equal to y. So this is the function notation on the left. The f is the name of the function. The value inside the parentheses is the x, or the input or domain value of the function. And the whole thing is equal to y. So either f of x or y is the output or range of the function. So if we use this notation, something like f of 4 means what is the output of the function if the input is 4. So if we look, when the x value is 4, the y value is 5. So f of 4 would equal 5. Similarly, if I wanted to know what g of negative 2 is, but my g is an equation, what I need to do to figure out g of negative 2 is plug in negative 2 for x. So g of negative 2 equals 3 times negative 2 plus 5. And then we just simplify. So g of negative 2 equals negative 6 plus 5. So g of negative 2 equals negative 1. So that's how we write this answer in function notation. We could also write it as the ordered pair, negative 2 comma negative 1, because the input was negative 2 and the output was negative 1. Similarly, if we know the output but want to find the input, we simply work backwards. So if we know that g of x equals negative 4, but I want to know what x is, I simply I take my equation for g of x, and I replace g of x with negative 4, and I solve for x. So subtract 5 from both sides, and then divide by 3. And we get that negative 3 equals x. Similarly, if I tell you that f of x equals 6, this works the same way, except here I have an ordered pair already given to me instead of an equation. So I go up to my ordered pairs for f, and I look for the one that has a 6 as an output, and that ordered pair is 2 comma 6. That has 6 as the output, so the x value is 2. We can also use function notation to write some operations that go along with functions. So for example, here I'm doing f of 3 minus g of 3. So what I first have to do is find f of 3 and g of 3. So f of 3, we simply go up and look for 3 as an input, and we find that 3 goes with 8, so f of 3 is 8. And to find g of 3, we plug in 3 into the expression. So g of 3 equals 9 plus 5, so g of 3 is 14. So then we can do f of 3 minus g of 3. So that would be 8 minus 14, which is negative 6. Notice that I find the values for f of 3 and g of 3 first before doing any subtraction. So why don't you all flip over to this next page, pause the video, and take a few minutes to answer these questions. Okay, now that you've had a few minutes to try these, let's run through the answers. Sorry, I clicked on the wrong part of the page there and made it fly away. So just like on the one before, f of 2, we find 2 as an input, so f of 2 would equal 6. To find g of 7, we plug 7 into the function, so it'd be 3 times 7 plus 5, So g of 7 is 21 plus 5. So g of 7 is 26. If we want to go the other way, and I know g of x equals 7, I replace g of x with 7 and solve for x. So 2 equals 3x, divide by 3, and we get 2/3 equals x. And if I want to do the same thing with f, I simply have to find the y value of 5 in my ordered pairs. So that's the ordered pair 4, 5. So x would be 4. And if I want to do f of 2 plus g of 2, I find f of 2, which is 6, and I find g of 2 by plugging 2 into the equation. So g of 2 equals 11. And then I add f of 2 plus g of 2 together. So 6 plus 11 is 17. So that's how we use function notation. Now, in all the examples here, we plugged in numbers for the functions, but we don't have to just use numbers. We can also use expressions. So, for example, if I have my new functions here, f of x equals 3x squared minus x, and g of x equals 4x minus 2, I can plug in expressions into that function. So, for example, if I want to find f of w, I just replace x with w. And as always, when you're substituting into a expression, you should always use parentheses, but then we can simplify to this one being 3w squared minus w. But I can also input more complicated expressions. So for example, I could find f of x plus 1, but it's exactly the same idea. I'm going to plug in x plus 1 for x in the function. So instead of 3x squared, I get 3 times x plus 1 squared minus, and instead of x, I get x plus 1. Substituting in parentheses, and now I need to simplify. So we can multiply out x plus 1, which is x squared plus 2x plus 1. And now we can distribute to get rid of the parentheses. So 3x squared plus 6x plus 3 minus x minus 1. And then we can combine like terms to get 3x squared plus 5x plus 2. And we can also substitute and then do operations. So for example, here I have g of x plus h minus g of x. So I can start by finding g of x plus h, which is 4 times x plus h minus 2. So g of x plus h is 4x plus 4h minus 2. And then I can find g of x, which we already know. G of x is 4x minus 2. And then I can find their difference. So I can take 4x plus 4h minus 2 minus 4x minus 2. Notice that I'm substituting into an expression, so I'm putting them in parentheses. So I distribute to get rid of the parentheses. So 4x plus 4h minus 2 minus 4x plus 2. And now I can combine like terms. So 4x and negative 4x cancel, negative 2 and 2 cancel, and I'm left with 4h. So that's the idea. So why don't you all take a few minutes and try these 4 problems on the next page. Pause the video for a moment, try these, and then after you've given them a try, you can start the video again and we will go through them. Okay, so now that you've had a chance to try these, let's go ahead and go through them to check and make sure you got them correct. So g of w, same idea as f of w. We just plug w in for x. So that would just be 4w minus 2, which we can get rid of the parentheses when we multiply 4 times w. So 4w minus 2. To find g of a minus 5, plug a minus 5 in for g. So that's g of a minus 5 is 4 times a minus 5 minus 2. So we just replace the x and g with a minus 5. We distribute and get 4a minus 20 minus 2. And then we combine like terms to get 4a minus 22. To find f of x minus 3, same idea. Except now we're plugging it into f, right? The name of the function, the letter in front of the parentheses tells us which function to use. So this will be f of x minus 3 equals 3 times x minus 3 squared minus x minus 3. Multiply out the x minus 3 squared to get x squared minus 6x plus 9 minus x minus 3. Distribute to get 3x squared minus 18x plus 27 minus x plus 3, and then combine like terms to get 2x squared, excuse me, I did not combine like terms correctly, to get 3x squared minus 19x plus 30. And then finally, the last one here is very similar to the last one we did together, except slightly easier because I don't have the operation between the functions. So just plug in x plus h into g, and you get g of x plus h equals 4 times x plus h minus 2, which is, when we distribute the 4, 4x plus 4h minus 2. Okay, so now we've talked about all the different operations we're going to do with these, and the last thing we're going to look at is an application that goes with functions that's very important, which is average rate of change. So average rate of change is simply the slope between any 2 points on a curve. So average rate of change is simply the change in y divided by the change in x. So that's y2 minus y1 over x2 minus x1. But now, because we're also talking about functions, we can also use function notation. So instead of y2, that's f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. So we can use either the y notation or this function notation. And hopefully the connection you're making as we do this is that this is the same formula as the slope formula. So we're simply finding the slope between any 2 points on the line. So this first problem says Wilson Sand and Gravel will deliver 12 cubic yards of gravel for $240, 30 cubic yards for $528, and 60 cubic yards for $948. What is the average rate of change of the cost as the number of cubic yards varies from 12 to 30 and from 30 to 60? So if I use some interval notation here, I want to know what is the average rate of change from 12 to 30, and I also want to know the average rate of change from 30 to 60. So to do that, we can simply plug it into our formula. So the average rate of change, the change in y over the change in x, remember this triangle symbol is the Greek letter delta, which stands for change. So I can take my y sub 2, which is the dollar value here, so $528 for 30 cubic yards of soil, minus my x value, my y value for my other ordered pair for 12. So for 12 cubic yards, it's $240 over 30 minus 12. And if you want, you can use your calculator for this. So that's 528 minus 240 divided by 30 minus 12, which is 16. So that's $16 per cubic yard. And notice the units on top go on the top, and then we're dividing by the units on the bottom. So dollars were on top and cubic yards were on the bottom. So then change in y divided by change in x. For the second example, now we're going from 30 to 60. So that's $948 minus $528 over 60 minus 30. Notice, just like with the slope formula, it doesn't matter which of the pairs I put first. They just have to match up. So if I put 948 first, 60 has to go first on the bottom. If I were to put 528 first, then 30 would have to go first on the bottom. So if we put that in our calculator, we get $14 per cubic yard. And so what this allows us to do is it allows us to compare over different regions and make some conclusions. So for example, in this problem, we can conclude that the more gravel you buy, the less you pay per cubic yard, because the average rate of change is going down as the number of cubic yards we buy gets bigger. Another example where we could use this has to do with changing speed. So in this case, it says Billy Joe McAllister jumped off the Tallahatchie Bridge, 70 feet above the water with a bungee cord tied to his legs. If he was 6 feet above the water 2 seconds after jumping, then what was his average rate of his altitude as the time varied from 0 to 2 seconds? So here we're going from 0 to 2. And so we want to put his height at time 2 on top. So his height at 2 seconds was 6 feet, minus his height at time 0, which was 70 feet, over 2 minus 0. Once again, it's important to get the order the same, but it doesn't matter which pairing I put first. So in this case, if I put that in my calculator, I'll get negative 32 feet per second. And so that's the idea for average rate of change. Now, in both those examples, I gave you the x and the y value. However, we could do this, if we look on the next page, with an equation. So for example, here, it tells me that if you drop a bowling ball from the top of a tower 144 feet high, the function h of t equals negative 16t squared plus 144 describes the height of the ball h after t seconds. To find approximately how fast the ball is traveling when it hits the ground, we can find the average rate of change of the height over the following time intervals. So, if I want to find the average rate of change from 0 to 3, what I first have to do is find h of 0 and h of 3. So we just talked about how to do that, but plug those values into the function. So this would be negative 16 times 0 squared plus 144. And this one would be negative 16 times 3 squared plus 144. You can do those by hand or plug them in your calculator, but what you'll find is that the y value for the first one is 144 feet, and at time 3 we get 0 feet. So at time 0 we're 144 feet, and at time 3 we've hit the ground. So now we can use our average rate of change function to find the average rate of change. So this would be change in y values. So y values at time 3 we're at 0 feet. At time 0 we're at 144 feet. So 0 minus 144 over 3 minus 0. And if we do that calculation, we get negative 48 feet per second. Okay. So go ahead and pause the video for a moment like we've been doing so far and take a little bit of time to try the other problems here. Okay, so now that you've had a chance to try those, let's run through the answers. So we already know what h of 3 is for all of these, but we can go ahead and find h of the other one. So we start by finding h of 1, which is negative 16 times 1 squared plus 144. Which is 128. And then we can plug it into the average rate of change. So once again, at time 3, the height is 0 feet. At time 1, the height is 128 feet over 3 minus 1. So for each one of these, we're just going to change the last value here. Okay, so that's 128 divided by 2, so that's negative 64 feet per second. And then we can do the same thing for all of these. So h of 2 is negative 16 times 2 squared plus 144. Whoops, sorry, not plus 144, minus 144. No, wait, I'm sorry, yes, plus 144. And so that equals So our formula would be, average rate of change would be 80. Sorry, nope. 0, I'm changing the wrong thing. 0 minus 80 over 3 minus 2, which would be negative 80 feet per second. H of 2.9 is negative 16 times 2.9 squared plus 144, which is 9.44. And the average rate of change is change in y over change of x is 0 minus 9.44 over 3 minus 2.9. So that's negative 94.4 feet per second. And then the last one, h of 2.99 is negative 16 times 2.99 squared plus 144, which is 0.9584. So that's change in y over change in x equals 0 minus 0.9584 over 3 minus 2.99, which is negative 95.84 feet per second. So, based on these values, we can see as the interval gets smaller, the average rate of change is increasing, and we can see that it's increasing to around 96 feet per second. So, we could say that when the ball hits the ground, it's going approximately 96 feet per second. So this has been section 2.1. Hopefully this video is helpful. If you found it helpful or not helpful, please let me know because they take some time to make, so I'll keep making them if they're useful. But hopefully this is helpful, and feel free to email me or call me or text me if you have any questions or need any help with any of these topics.